Okay, so we'll do the profiling then. Um, so the profiling, nearly always profiling with perf on Linux perf. So the top line here is just the most straightforward case where, let's say, we're profiling LibreOffice itself directly from when it starts. Perf record, and then I tend to explicitly put in this that I want to record things with the dwarf mechanism and then limit it to this amount of data recorded per line. So it's become habit to use that one. If you leave it out, you'll still get decent profiling, but with it in, then I find it works better with optimized builds where you have the debug info installed and available. That I find that Dwarf works better for resolving symbols than any of the alternatives. So I tend to just copy and paste that into all of my perf calls. Anyway, in any case, the output is in perf data once you finish profiling. And then there's a whole bunch of tools that can operate on that data. There's a command line one, perf report. There's a graphical one, hotspot is what I tend to use. Or we tend to take that data and we tend to visualize it as a flame graph. But this incantation here is your most basic version of that, which outputs you an SVG so you can have a look at what things are. So just this is the command line one, or whatever text-based one, which I never use basically, but it exists and you can tunnel down to the things. So if you were in a particularly extreme point of thinking mode, you can do that, but I never do it. There's Hotspot, which is a graphical one. I do use this one occasionally when I want to tunnel down into one particular thing that I want to look at. You can look at what calls what. You can double click on things. You can look at the source code, and you get little annotations beside the lines of source as to what percentage of your time is taken on this particular line of code. When you're down to micro optimization land, I tend to look at hotspot output for it. But for the most part, we take the profile data and we turn it into a graphical visualization, these flame graphs. So this is one from from LibreOffice, and some formula calculations and a little hotspot there. We'll come back to that in a minute or two. But so most of the work is done starting with Flamegraphs. That's the author's website for Flamegraphs, Brendan Gregg. Search for Flamegraphs and Brendan, you get there. He has a book. I have that book, Systems Performance, incredibly useful. And he has a presentation, many presentations on Flamegraphs, and one of them is listed there, and it's a far better presentation than this one. So it covers all these topics and in-depth, detailed stuff that is particularly well presented. Anyway, on the flame graphs, what matters is that the widest thing is the most significant thing. So you look at the graph, and whatever is widest is the thing that you're going to be most interested in reducing its width. That's all you have to do. Make the wide thing narrow, and you have succeeded. The order how they are presented left to right in these classic flame graphs is irrelevant. It's just alphabetical. So left to right is not a timeline. Left to right is of no significance. And the colors themselves then are generally not significant. It's just so you can tell what's one entry from another apart easily. So all that matters is how wide they are, and then it presents as to what calls what vertically. So we'll look at one of those in a bit. Flame graph output is SVG. There's kind of interactive stuff built into the SVG. You can click on an element and it'll expand that to give you an expanded view of what you've clicked on. So you can click in and out to zoom in and zoom out. There's a search option where you can search for things that you see on it, and then it'll highlight those and add up the percentages of those things. So if you see something that looks somewhat significant, you can search for it, and then you'll see all of them highlighted, and it'll accumulate the numbers together. So if you see that something is 5%, but you've got 10 of them, you can quickly find out that that's where 50% of your time is going, and it's worth your while optimizing the 5 small things because they're actually one large thing. Anyway, so we'll just look at a sample flame graph just to show some of the interactivity. This is the one that I showed earlier. So we can click on one and it'll expand out like that to see where the time is. So if we click on back to all, it'll shrink back. So this is like a calculation going on here. We can see that most of our time is spent on this get cell value or 0. What is that doing? Click on it, you click in, and you see that there, in this particular old case, a lot of our time is actually stuck on acquiring mutex as we're waiting on ourselves for the most part. There's other threads working on the same area. So you get a pretty good overview of what's going on, and you get a feel for that the solution for this problem is likely that you need to do something to reduce those mutexes. With the searching then, we'll just, let's say we search for SV number. And you can see that all these things have been highlighted here, and then that the percentage of their accumulation over here, 26.6% of the time is spent in SV number related things. So that's your basic interactivity in those flame graphs that I was mentioned. That's that. So there's practicality with all these things. So a lot of the things we do is profile the individual kits in online, and that's pretty tedious because there's one of those per document, and you could actually have dozens of documents open, and it's hard to find the right one. So there's a script inside the online source code. That script's profile cool. It'll do all the tedious work of searching through all of the kits, finding out what file they're open for and what people are looking at the document. And you can use that to select which one of the kits to profile. So that's done weekly inside in the QA calls and in the cool calls when we're testing Clara online, and we're doing profiles of that. So it's running that script and getting these flame graph outputs. Well, what I've shown works in all the current Linux releases. It's just straightforward, just Linux perf record and perf script. But in some of the older distributions, I found that there's various problems that have been worked around. So the output of perf script can be super slow on some of the older perfs or some of the distributions, and I tend to add in this minus no inline when I'm doing that. That tends to speed up the generation of things quite a lot. So if you're finding it very slow to generate the output, you can do the same thing. The actual output itself is massive. This isn't really all that important when you're doing a relatively sharp profiling. So some of the things we like to do is profile things for a week. Once you start doing that, you end up with multiple gigabytes of stuff, and it becomes very difficult to manage. So what you can do there, then you can reduce how frequently you sample. There's a minus F option for that. Things like that to reduce how much data you collect, and you get less fine-grained information, but maybe it's more useful for the longer trends like that. And also then perf theoretically has the option that you can pipe mode for generating these things. We only want a small amount of the data that is actually recorded, vast quantities of data recorded. We need a small bit of it, but it isn't very straightforward to ask perf just to give us the small bit we need. We get everything. If we could use this pipe mode in perf, that would avoid the problem, but it doesn't work on some of the older Ubuntus. There's another option then to switch output every 100 megs. That seems to work reliably on all of these other distros that we're doing the profiling on. So there's another script inside an online. This script's perf record stack collapse. And then that will call perf to automatically dump every 100 megabits the vast perf data and convert it into this much smaller amount of data that the Flamegraph process needs, and do that incrementally as you go along. So a lot of this long-term profiling that we're doing has been turned over to using this perf record stack collapse, which does this thing. So again, if you're doing longer-term profiling, you'll see a script there that makes that practical to do. And there's some commentary in that, again, about some known bugs in some versions of perf that exist out there where things will hang. And then there's also documentation included as how you can build your own perf to use against a distribution where this bug issue, where this bug exists in the supply version. So in general, everything works fine, but when there comes to problems, you can find solutions to those problems in the two scripts mentioned there. So what profiling do we do? There's links there to the weekly profile I mentioned earlier, which is just your regular CPU flame graphs as to where time is spent, and we get an overview where that is. And then there's this other GitHub repository where we're putting these more specialized profiles. There's this long-term one I mentioned earlier where we just profile to see what happens on our demo sites, and we do that for an entire week at a very low frequency, and we get a kind of an overview for what does col.la Online and its kits do over the course of a week. In some cases, that seems to be converting PDFs is what seems to happen there. Importing PDFs, perhaps for thumbnailing purposes, it seems to be a major use of it. There's another one, this watchdog profiling. We'll come back to that in a bit, where you're trying to find where there are stalls, interactivity stalls, when you do something and there isn't a response back to that in a short period of time. We detect where there are these kind of glitches, these little stalls. And then there's a very specialized one, this WP page one, where technically complicated, but fork each kit from another kit, and if there are writes to the original kit pages, we try and detect that to see why are we modifying our original kit in the subkit, what bits of it does a new kit need to change to be different from its original one. So that exists in there as well. And Perf can record like CPU events for the most part. That's what you're generally interested in. You can just record what is your process doing, but you can specialize and you can perf on other things as well, and back to that later on. But one of the things you can search on or profile on specifically is system calls. So you can profile a particular system call. You can do that per process. You can do that per system. So for these watchdog stalls, what we do is we have your event loop inside the kit, and if there is no response after a certain period of time, we fire something from this watchdog thread that perf can detect. And what we use is a syscall that nobody uses anymore. Then we profile system-wide on this FU time set syscall that nothing else uses. And if we profile just on that syscall, we will find all the cases, what everything is doing when that syscall was triggered. And by looking at that, then we can detect all the times that this particular backtrace indicates when something has stalled because this syscall was triggered. So we get an overview of all the little parts of the code which are not quick to respond, whether they need to be broken up into smaller sequences or whether there's a small hang in there of some kind. So this is how you record on a particular syscall, the -e event, and then there's syscall, and you can trace individual syscalls. You can also trace things like page faults, which you could use to detect when is a process growing in memory, and you should be able to get a backtrace as to why something is growing, at least a rough overview as to why something is growing in memory. The other thing that we looked at a while back was trying to improve calc threading performance, and we generally kind of I stumbled into the finding that we were spending some of our time with contended locks on very basic atomics. So if we'd had like two strings that were shared between two processes and all they had was a little reference count number, we were spending an awful lot of time just incrementing that share between threads reference count. And the question was, could we just isolate that on its own in a profile? Could we profile just for contention? And the long way around, we found that the right way to do this then is we do perf list -v. It'll give you a list of the thousands of things that perf can profile on, not just the standard ones, but all these obscure mini little ones as well. And tucked away in all of this is basically copy and pasted in there from the Intel documentation for what they provide, is that you can sample how much contention there is for synchronization between threads, and the documentation then would suggest this particular line, which you can then convert into the equivalent perf line or perf recording. Now you're just recording only where all of the contention appears. So if you do that and you go back to our original threading thing, you can, well, the region trading at the time, you can see these are the places at these RTL string requires here and here. These particular cases are where there was a string shared between processes, and it is a significant amount of time has been spent on just incrementing their shared reference count. And in this particular case, if you investigate that a bit further, you can find that in this one particular case at least, if you change this into, instead of querying for the string, doing something to the string and taking a result from it, if you visit the string instead, if you rewrite your code so that it goes to the string and doesn't make what should have been, in theory at least, a cheap reference count increment, but if you avoid that increment, you get a significant speed up for that. So that's how you can find the contention on its own. More recent things, which is maybe something I'm more interested in now, is doing kind of finding out where our memory is and getting a view of where the memory is used up. Now, what I'm not interested so much in is where do we allocate from, which you could do straightforward enough with perf itself. But as to where is the live memory, where is the memory that is long living, where was that allocated from, and why was it allocated, and you get a view for that. So I've been finding what works well here is to use tcmalloc, which you can even LD preload before an existing binary without having to compile anything. Set some environmental variables, and that'll dump stack traces of where your allocations came from. So that is initially fine, but the output from tcmalloc is suitable for this other profiler that I don't really use, and it recommends these kind of outputs. So if I look at what that kind of output looks like, what we'll see is this is, for instance, the kind of profiling output from this alternative one. This is the large canvasy panel thing that you can scroll up and down, and there's stuff in there, and some things are big, and this is useful, but it's not as kind of immediately straightforward as you'd like to see. So that's the pprof output. I'm going to do a bit better than that. Here's a little section of it there again. What we want to do is turn that into a flame graph, as we did for everything else, and have a look at that again. So pprof has a collapsed option, it turns out, which ManPage doesn't mention, but exists and works. So if you use this pprof collapsed option instead, you could run the output of that through Flamegraph. And here you'll see that there is this additional option for saying color as well. It doesn't have any real significance, but it just uses a different color theme. It's just become kind of semi-standard that you would use this greenish mem theme for memory profiles. So what does that look like? That's what this output here is the same as this output here, except as a flame graph instead. This is a empty writer document. I think we can look at that as the actual original flame graph here now. Yeah. So if you're ever interested in where is the memory going in writer or any kind of a blank document in LibreOffice, you can find, interestingly enough, that when you, and the numbers reported here in the tooltips are in bytes, so that's 20 megs there. The 20 megs are here. So once you start writer and you fill the autocorrect dictionary, fill the list of autocorrect dictionaries, it'll do this is valid BCP 47, which takes the liblang tag stuff, and it loads up the XML file that comes with liblang tag, which has a whole bunch of special tags in it for indicating variants of languages, which I'm sure 99.9% of people never use. We can also see that it's not just there that this happens. It happens in a few places. Over here is the autocorrect again, similar one again. But there's a lot of language tag parsing of its own internal database, which ends up using 20, 30 megs straight away. So that's clearly not right or not great, but that's where your memory is in a blank writer document. Now, it makes sense that the main window inside in writer would require a reasonable amount of space, something to actually render your document into fine. And then over here, we'll see that the font name boxes, presumably for the previews of the fonts that are shown in the drop-down list of the name box. Again, there's a significant 14 megs of space used up for that. So where your space is going in a writer document is the writer document itself's canvas that it draws in. That's reasonable enough. This unusual liblang tag database for various weirdness there. And then the combo box previews as well take up a lot of space. So yeah, so that's where that memory is. Then similarly, if we do one for col.la itself, not the kits, but the actual server itself, and just after it's been started up, a debug version of it, interestingly enough, it finds out that 99%, basically 98% of memory is consumed by this file server request handler hash of the files that it loads up during startup to send out from memory afterwards when queried. So most of the memory is used up. Vast quantities of memory, 235 megs, are used up by this standard map. And as it turns out, and most of that memory is actually basically dead memory. And if you use, as this commit up here does, if you use shrink to fit on the various strings, you reduce this 235 megs to about 50 megs. So once you have some tools to actually look at things, then you can quickly, easily see where the memory is going or where the time is going. And you can use these to get some ideas as to how to improve things. And yeah, that's it. Any questions, I suppose?
Thank you, Caolan. Okay, now time for questions. A short question.
I have, yes. Great stuff, Caolan. Thank you. Can you maybe go back to the very first slide? Have you tried, instead of dwarf, enabling LBR for the call graph? Yeah, dash call
Yeah.
graph LBR.
No, I've never used the LBR one. Have you had any
Yeah.
success with that?
Yes. So LBR is it's much faster. The the perf files are significantly smaller, and creating processing those files is also much faster. So if you run script or you run even just report, it's, I don't know, maybe 5 to 10 times faster with LBR. The problem with, you have two problems with LBR. One, obviously, you need a hardware that does support it, but pretty much any recent hardware will. But the other thing is that it doesn't give you very deep stack traces. There's a cap because it's hardware trace. So you would typically get no more than about 16 um, frames at a time.
Yeah.
So if you look at those very deep, 30, 40, 80 calls, you won't see them. But for a very quick and sort of rough granularity view, it's fast, it's convenient. So I tend to go for LBR first and then dwarf.
Hmm.
Worth trying.
Yeah.
Um,
Yeah. That's
the other thing is speed scope. Heard of that?
not really.
Okay, so speed scope is an open source flame graph visualization. It's a web application. Actually, you can use the public one or you can run it yourself. It shows you so you run the last command you have there with perfect script. Yeah, you get the output, but you don't go through the flame graph scripts. You just dump that into a text file, and that's what you load it in the speed scope. And it has three different views where it gives you the flame graph, but it also collapses the flame graphs into aggregate view. I think it's called left heavy, where you see basically all of the long running functions collapsed, aggregated together, right? So it's a very quick way to see the functions that, regardless of when they were called and how many times, and each time how long it took, it's basically aggregating them and showing you which functions are really taking the longest in a flame graph format. And then the last one is you get a traditional perf report style view where you can sort by the self time and also the call chain time for every function.
Yeah.
So it's really convenient. It's fast. You don't need to fiddle with the scripts and then get an SVG. It does it for you. Just give it the output of per script, and it renders these three views in the browser in a very convenient way. And obviously, you can zoom in on any time frame individually. You can go back and forth. Anyway, it's really convenient. Is what I'm trying to say. I use it rather than the original, flame graph Perl script.
Yeah, indeed, yeah. Yeah, and as I mentioned earlier, something like Hotspot will give you the interactive flame graphs from the perf data as well. And yeah, if you start using something like VTune, you can end up with flame graphs in there as well, and a whole bunch of options. But I think that also backs up onto perf basically as well, so you're not missing out on anything using that.
Yeah.
I didn't mention, because it's not really covered here as well, is that there's also the browser profiling things as well, that is perf options. And again, there you tend to get kind of similar kind of visualizations there as well.
True. True. Okay, if you move ahead with the slides, I'm gonna remember other comments that I had. Yeah, hold on. I was wondering how we run perf on for the week long. Are we running cool WSD under perf so that we get all the children, or like what is the approach here?
I think on that, what I have to recall exactly. No, that's for the entire system. Yeah, we
Okay, so
run the
it's for
entire
all.
system
Got you.
and
Yeah,
we
makes
filter
sense.
out the ones that matter to us. And yeah, that's what I want to mention as well, is that the data that's fed into FlameGraph, it's just a really kind of basic text format in the end, and it's like can be manipulated in whatever ways you
Sure.
want. For example, all of our kits have individual names like kit this, kit that, kit the other, and
Hmm.
for the purpose of flame graphs, we just merge together all the kits as one kit broker thing, and the same for background saves and everything. They're all just accumulated together because it's trivial to do that. So yes, the long, I think those three examples, they're all no, yes, they're all system wide. So what
Right, the
happens is that,
dash A
yeah.
or something equivalent. Okay. All right, that sounds good. Skip ahead. Yes, this one. Um,
Mm,
so Perf is really convenient for giving you the list of all the performance counters that it recognizes by name, and it knows how to calculate them, because some of them are actually calculated. They're not real
yeah.
counters, right? But you really don't need to be limited by whatever list dash V gives you. If you know the exact processor model that you're running, you can look up the available performance counters, and even the ones that aren't available in perf, you can pass the individual mask and ID for the counter itself to perf, and you can enable them. And in fact, you can give them a name. So
Mm,
you basically can do exactly what perf has hard coded in its list of available or recognized performance counters after the fact, right? By simply giving it individual IDs and masks and tell it call this XYZ, and that's what it's going to call it in the reports, and it's going to enable it if the hardware supports it. So you're really not limited by what perf list gives you. Although it's really convenient if you know something is already named and calculated for you, that you don't need to worry about calculating it from the raw numbers. So
Well,
that's really convenient.
yeah, I think the idea, like, of knowing your perf counters intimately, on your processor model is not something that that comes easily to me for
Yeah.
sure. And what I found most useful with perf, because perf list will list things, and I was aware of that, but I wasn't fully aware of that if you perf list with the V, that basically you get what looks like the Intel documentation of what these things were for in the first place, and that I thought was the most useful part, is that getting a whole list of things to that you can perf on is great, but getting as to what they're actually useful for, or what you're looking for. So if you do the perf minus V and you search for congestion and you find a few things in there, and then you go off, you can use them, and then you get data kind of output that matches your
Yeah.
expectation. It's
So
super cool.
right. So on the point about knowing the hardware, um, this is the website you need to go to. It's perfmon-events.intel.com, and it gives you, at least for Intel, right? I don't know if there's an equivalent for AMD, but definitely the documentation is there. But this website is very convenient. Obviously, this is an Intel official website, and what it gives you is per hardware a list of all the available counters and a description of each, but you can also search. So you can filter the list and you can find if your particular hardware has it or doesn't have it, and what is the equivalent or something like that. So, some of the counters, by the way, over the years, they were made into their own full-fledged counter in the hardware, but previously you could have gotten to the same approximation, let's say, through other means that were crude, but they were still available. Some of them are hinted at in that documentation. Anyway, that's the way I find the interesting ones, and yeah, it's very convenient actually with the search facility there.
Yeah, the change over time of what counters are available, or their names, or something like that, is something I've noticed in the various documentations. That you'll get some documentations that'll say it's called one thing, and then you'll see that it's actually been updated to be something slightly different. With maybe, I don't know, in this particular
Yeah,
case, I think it's
yeah,
one particular thing. It might have been XXSNP might have been the only thing that existed in the past, and now they split it into two different things. And if you just use XSNP, it's not documented, but you get both of these things together. Just provide you the
right.
one that's shown pretty shorter and kind of under. Anyway,
Yeah,
yeah, that's pretty
and the fun gets even better when one realizes that there has been bugs in some of these. So there has been cases where counters have been known to report the wrong thing in the hardware, that might have been fixed with a subsequent firmware or opcode upgrade um, that you may or may not have. So you need to actually check
mm,
uh, the individual patch level for the firmware of the processor to know if you have it or you don't have it, the bug, or conversely the fix for the bug. So yeah, this can be very, I mean, obviously, and there are like literally thousands of these, right? So
yeah.
the rabbit hole can really go very deep if you chase it.
Indeed.
Okay, um yeah, let's skip ahead. I don't know if there was anything else. Yeah, I wanted to highlight that I did notice some of the ones that you've noticed in the flame graphs. Obviously, the file server cache, that's one that is very prominent. Um, but running LSAN does actually show all the memory allocations in the kits, and I suspect that is because we forcefully exit with under exit, and we never get to cleaning them up. So that has an advantage in that you can actually see all the allocations we've done and where we've done them very easily. You just build with ASAN, which gives you LSAN, and then you open a document, play around, and when you close it, you get this megabytes of memory allocation stacks and whatnot. And I do see that the language features are very prominent in those reports. We're allocating large amounts of memory just for the language features, and it's very clearly visible there. And I found that that's the easiest way to see what allocations we have without really doing anything more than just rebuild with and rebuild not all of sorry, not rebuild core with the sanitizer, just building online with the sanitizer gives you um, leak reports for everything, including core with the stack traces. You only need to have it built with debug. That's it, and you get it for free. So it's very fast, very easy, and you see what's going on.
In the online course, the language tag thing itself, theory is at least that it's loaded once in that for kits. So you take the hit once, and then the eventual kits don't need to duplicate it. So there is that 20 meg is being reserved in the online case too, but hopefully just the once and not duplicated per kit. But yes, I hadn't thought of the LSAN, but at the same time, what I was kind of mostly aiming for was a full release configuration mode thing that you would then have to do the minimal amount of kind of modification to check something that's as absolute close to release configuration as possible to avoid any kind of fusion.
Yeah. Okay, I'll stop. I don't want to take the whole time. This was fascinating. Thank you. Thank you.
Thank you, Ash. Thank you, Caolan. Attila?
No questions, thank you.
Berem? Darshan?
No questions. Thanks, Kellen.
Gokai? Who's okay? Hussein? Okay, we couldn't hear, but I guess it's no questions. Jaume? Joao?
No questions, thanks.
Mike? Okay. Miklos?
I would have one question. I guess on some slides nearby, you had this sample where the JavaScript file caching map was consuming some 200 megabytes, and with a one-liner fix or like a short one, you decrease that to something like 50 megabytes. Yeah, I see the function names here and the percentages and so on, but how did you know what was the actually used amount of memory? Is that visible here and I'm just blind, or that's something that you observe elsewhere?
Well, I did it two ways. First one is that when it comes to this memory profile of the TC malloc output, the numbers here refer to bytes. So if I just hover over this line here, this clip,
okay, so samples is actually bytes in this context.
In this context of the output of the mangled output of TC mallocs dump into this, it happens to be that's what way they present it is in bytes, which is super convenient. But I didn't trust that one bit. So I added in a where we had this dump state, I added something to additionally dump the state of the hash map, and then to go through the entries of the hash map and output the capacity of the strings and all of them, and add those together and output. And I was getting indeed the 240, 230 megs claim of capacity of the strings in the hash map. And the one-liner fix is just to use string shrink to capacity on every entry in the hash map once it has been built, and that takes me down to a reasonable, a smaller amount. That said, this is for a debugging one where you have, all the source inside in your whatever dist directory, and this caches everything in your dist directory. And it's just something that happened yesterday. I haven't really any visibility if it makes any difference in an actual release version. Quite possibly it's far less significant there, but just a bit startling when I went to look at where the memory is in a col.la and found out that it's totally consumed by something I didn't expect.
Yep.
Makes sense. Thanks.
What is really interesting is that so just literally days ago, I also saw this when I was looking at the memory profiler, and my first reaction was, yes, we know about this. This is the file cache. Obviously, it's going to be, whatever the number is. But what is interesting is that you checked the actual size with the memory consumption, and you figured, hold on, there's some slack here. Let's pull it back. Whereas I didn't. I just looked at it and said, yeah, whatever the number is, it probably is right. Because we have to keep all the files in memory, and it's gonna come out to some huge number. And I didn't check. So yeah, good stuff.
Yeah, it was mostly because I just didn't trust any of the tooling, and I had to manually check it for myself.
No, that's the right way of doing it. That's double check, triple check. Yeah, absolutely.
Okay, thank you. Miklos, do you want to add something else? Or
No.
Okay, thank you. Pranam,
No questions. Thank you.
Rash, Timur.
Yes, I have a not question which is not directly related to the topic, but to the consequence.
Mhm.
So, for example, if something is seen as especially resource demanding, like that example of drop-down previews, should we introduce an option, let's say in col.WSD, to facilitate, let's say, better performance for those who don't care about nice visual style, but who prefer more to have, let's say, faster or less demanding product?
Well, I suppose some of it is like kind of philosophy and all the rest of it. I mean, I'm not a fan of adding options to things. I don't like adding options to anything, because then you've got just every option kind of doubles the amount of things you have to worry about. So I prefer not to have an option to turn something on and off. But for example, those previews, it's probably the case that most documents have the same subset of fonts. So if we were to generate the previews in this original fork kit before we fork, then we might be able to have one copy of the previews in all of the kits ready to roll, and then there would be basically no cost per document, and they'd be already generated and fast. I mean, the profile here that I'm looking at is the one for standard desktop LibreOffice. I didn't really double check to see what the story is in a kit case. I just wanted to show a desktop version here and an online thing here. So I don't quite know. I was looking at this a while back, that the font name box is using up space in online as well. But in that case, it seemed to be less the pictures and previews and more the actual list of font names itself. So there is a problem in online, and I had a patch that just merged to improve that. So anyway, in general, I'd hope not to add options, and hope that we could just do something that's better for everybody without making it more complicated for ourselves.
Thank you.
And Justin? No questions. Okay, thank you, Caolan, and thank you everyone for joining. See you next week, and bye-bye.
Thank you.